So this is a mini lecture series on the significant worldwide problem of arsenic pollution. And in this lecture, I'll be going through an introduction to arsenic and its importance. So I'll be talking through the health implications of being exposed to arsenic and trying to describe and explain the global distribution in groundwater. So arsenic can be an extremely dangerous chemical, and it's been used for its deadly properties throughout history. And sometimes referred to as the king of poisons, its presence in groundwater has impacts to the health and livelihoods of millions of people worldwide, and particularly in South and Southeast Asia. So arsenic is a geogenic pollutant, but there is some evidence to suggest that human activity, such as groundwater pumping, may influence its release and transport. So the objectives are to become aware of the scale and importance of arsenic pollution, and then to explain the health implications of drinking arsenic contaminated groundwater, and then to know the major controls on the global distribution of arsenic. So some background into the problem. So although the toxicity of arsenic compounds has been known for thousands of years, the presence and implications of high arsenic in groundwater has been increasingly realized in the past 50 years or so. And the WHO guide value is 10 micrograms per litre for drinking water. But it's important to note that this is only a provisional value, and some areas are targeting lower concentrations in drinking water to perhaps 1 microgram per litre, such as in the Netherlands. Now, this map has compiled a number of studies and shows where arsenic is exceeding 10 micrograms per litre. And as you can see, there's a number of reported cases in North and South America, the Ganges, the Bay of Bengal, and the Shanxi province, and also the Red River Delta in Vietnam. And it's important to consider that this is only a compilation of actual reported concentrations. And many areas of high arsenic have likely been missed from this map, as we will discuss later. So I picked out some of the worst affected regions by population exposed to groundwater exceeding the WHO arsenic guideline. And this does not correlate necessarily to the distribution of arsenic. So if the population is not actually exposed to arsenic, then it's not actually a problem for them. And for example, many supplies in North America are centrally treated, which could explain to some degree why it does not have a larger population exposed to the arsenic, yet their groundwater appears to be heavily affected by it on the previous map. However, arsenic can still be a challenge in untreated or private water supplies here. So the top 3 countries here are Bangladesh, India, and China in terms of purely number exposed to arsenic. And overall in the world, an estimated 94 to 220 million people are at risk from arsenic poisoning. And it's thought that about 80% of these people are found in Asia. So we've talked about who is affected and where, but what about the exposure pathways and the health implications of this? So when we talk about exposure to a chemical, we can refer to acute and chronic poisoning. So acute exposure means at very high concentrations over a short period. And for arsenic, this can lead to muscle cramping and potentially death if the concentration is high enough. Unfortunately, there are extremely few cases of acute arsenic poisoning worldwide, and to have this concentration naturally is fairly unlikely. What we do have to worry about more commonly is chronic exposure cases, which occur at lower concentrations over longer periods of time. And the biggest concern globally is arsenic contaminated drinking water. And this could expose a person to high arsenic through the drinking water itself, which is often taken from a tube bar as shown in this photo. Now, rice often contains elevated levels of arsenic, especially compared to other cereal crops. And the consumption of rice is considered a major exposure pathway for arsenic for many people in the world that consume it. And then perhaps less commonly, but worth mentioning, since arsenic is used in many industrial processes, workers who work in these industries, like textiles or preservative production, may be subject to chronic exposure. So I've listed some illnesses and problems that are triggered by arsenic exposure. And I've grouped these into respiratory, neurological, dermatological, and cardiovascular issues. So arsenic can trigger a number of diseases and cancers through the body, but it's often difficult to attribute these to arsenic in particular. So there's no method to distinguish cases of cancer caused by arsenic from cancers induced by other factors. But perhaps most distinctively to arsenic, arsenical keratosis is a growth of keratin on the skin caused by arsenic. And I've shown a picture of that here. So arsenic exposure has also been linked to Blackfoot disease, which is a severe disease of blood vessels and can lead to a condition known as gangrene. So we can look at the arsenic affected areas of the world and try to understand what environments cause this natural enrichment from background levels. So high arsenic aquifers are typically found in alluvial basins. And these basins can be characterized by high weathering in the upper catchments, with the delta being cut into deeply. And these areas are also humid and the organic matter content is generally high. And we'll talk more about organic matter and its potential links with arsenic later. So this describes the general occurrence of high arsenic in groundwater. But what about more detailed predictions? So perhaps a more recent take on things, we can now predict arsenic occurrence in groundwater based on modelling. So there are a number of ways in which we can model arsenic concentration where it's not been directly measured. And generally, the input data here includes various climate and soil parameters, geology and topography. And that's exactly what has been used to generate the prediction maps of Southeast Asia here. And the model calculates the probability of groundwater exceeding the WHO limit of 10 micrograms per litre. And you can see the differences in colour correspond to how likely this might be. And at this point, I'd like you to introduce yourselves to this useful resource on groundwater assessment and where this image was visualized from, and that is GAP maps. So GAP stands for Groundwater Assessment Platform, and it compiles a number of studies on arsenic vulnerability at various scales. So as well as arsenic, GAP maps contains models on groundwater fluoride predictions and maps on surface properties. And this includes soils and geologies. So you can use the site freely using this link, and I recommend you have a look at what it has to offer. And we've discussed the occurrence in groundwater and how it might be predicted. But what are the underlying processes on arsenic mobilization? Well, there are thought to be 4 dominant processes that can cause high arsenic to form in groundwater. And the majority of high arsenic cases can fall into one of these. So these are reductive dissolution, alkali desorption, sulfide oxidation, and geothermal. And out of the 4, reductive dissolution occurs most commonly, particularly in shallow aquifers of South and Southeast Asia. And alkali desorption also plays a significant role in some settings. And this is a map of Southeast Asia according to which processes are dominant. And here you can see the reductive dissolution setting closely maps the route of some of the largest alluvial basins in the world, including the Ganges, the Brahmaputra, the Indus, and the Yellow River. And these regions correspond to a higher probability of very high arsenic in groundwater. So alkali desorption is arguably the next most important mechanism worldwide, perhaps more in South America, but you can see a few areas of that in the map. And there are also some areas where geothermal activity causes higher groundwater arsenic. And the sulfide oxidation mechanism is much less common in this part of the world. And just to quickly summarize the distribution in Myanmar, groundwater arsenic levels are generally low across most parts of the country, except for the Irrawaddy Delta in particular, as well as some localized areas. And a recent University of Manchester-led survey in collaboration with Myanmar partners found that 14% of groundwater samples from areas within central and southern Myanmar were found to exceed the WHO provisional guideline of 10 micrograms per litre. And the link here to this open access publication provides more information on this. So to summarize, arsenic is a worldwide problem, but it's most significant to populations in South and Southeast Asia. And chronic exposure from arsenic contaminated groundwater can lead to a number of respiratory, neurological, dermatological, and cardiovascular issues. And we can roughly predict the occurrence of arsenic based on river basin type, and to a greater extent from surface characteristics such as geologies and soil. And all you need to know for now is that there are 4 methods for arsenic occurrence in groundwater, and these include reductive dissolution, alkali desorption, sulfide oxidation, and geothermal waters. And we'll talk more about some of these in the next time, where we'll be discussing the geochemistry of arsenic. And for the learning exercise, if you could please answer the following questions. So for the first question, I'd like you to summarize the health implications for chronic exposure to arsenic contaminated groundwater. And secondly, what is the expected predominant mechanism for arsenic mobilization in the lower Irrawaddy Delta? And can you say where else this mechanism occurs in the world? So here's a list of references used for the slides. and some further resources. So please refer to the best practice guide for arsenic in drinking water, which has some freely available chapters in it and has some very useful information on arsenic. Please note the disclaimer and conditions of use for these slides.